Thanks. Hi, I'm Bill Koish. I'm from McGill University in Montreal. I'm a theoretical physicist, and I work on understanding how I can use nanoscale systems to improve future information technologies. And in particular, I focus on the quantum properties of these nanoscale systems. Um, with my group and with the help of organizations like CIFAR and the provincial organization INTRIC, I try to talk regularly to people who are doing computer science, people who are doing experimental physics and engineers, and try to understand, exactly how we can exploit quantum mechanics to improve our technologies. And of course, quantum mechanics has been around a long time. This is a 100-year-old framework that allows us to understand nature. Many of you know that we need quantum mechanics in order to describe something as simple as why a metal glows red and then hot, and then white as we heat it up. This is a consequence of the Planck blackbody spectrum. And quantum mechanics also underlies a lot of the technologies that we use. And we heard about this earlier from the talks, actually several talks, where we heard that, for instance, lasers and light-emitting diodes require quantum principles. These are the systems that we use to pump pulses of light through fiber optic cables for communication and information technology. Quantum mechanics also underlies all of the different electronics that we would want to use. For instance, the high mobility transistors that were mentioned by Thomas earlier that we use for wireless communications. Quantum mechanics underlies many of these different systems, including, say, memories. Flash memory requires quantum tunneling of individual charges. All of the magnetic memory that you might want to use, in principle, uses quantum properties. Magnetic resonance imaging is actually an image of what is a quantum property of individual magnetic moments, so quantum coherence of individual magnetic moments in our brain. But all of these examples sort of only use quantum systems in a way that simulates classical behavior. We can think of these individual magnetic moments as little bar magnets, or we can think of the individual charges in flash memory as like a billiard ball that you would place in one pocket or another. Quantum rules allow us more. So quantum systems, unlike classical systems, can be in some sense two states at the same time. This is called superposition. Quantum systems exhibit stronger correlations than any classical systems, known as entanglement. And by exploiting these quantum rules, we can get behaviors that are not possible for any classical system. To understand where this comes from, you can just count the number of classical bits that you need to describe a quantum state. It turns out that in order to describe the quantum state of even 30 or 40 quantum bits, you need about a terabyte of memory. To describe the state of 300 quantum bits, you need more memory in bits than the number of atoms in the visible universe. Quantum states are fragile, and they can be destroyed just like information in your hard drive. But quantum states offer the potential for several different types of technology, including quantum simulations of biomedical systems, quantum communication, which is a way of communicating using cryptography that is limited by the laws of quantum mechanics, and quantum computation, which can allow you to solve, in principle, an arbitrary problem using quantum systems. There are many spin-off technologies that have come out of our study of these quantum systems, including improvements to clocks, ways to build better nanoscale sensors, improvements to our understanding of how birds migrate, and how photosynthesis works. So what is my personal role in this? Well, I work with my students and postdocs to try to exploit what we understand about theoretical principles to use entanglement and superposition in real nanoscale systems. So we're theoretical physicists. Our day begins and ends typically at the chalkboard or in front of a pad of paper with a pen. And our research is fueled really by enormous amounts of coffee. But we can't do it alone. We also have to rely on our experimental colleagues. So our experimental colleagues design complex apparatus and try to decipher our complicated equations in ways that transmit, that information into some kind of physical, real thing. And in converse, we also enjoy having our experimental colleagues tell us what new result they've found, and we try to interpret it. So an example of one of these experimental systems is a quantum dot, where you spread an electron over many atoms, but at low enough temperature, you can have a single electron with only two possible states, a spin up or a spin down. And those two states can form a quantum bit. So one thing that we've looked at a lot is trying to merge our understanding of quantum dynamics, the way that a complex quantum system behaves as a function of time, to improve the measurement of quantum systems and the interpretation of those measurements. And so we've combined ideas of classical information with our understanding of the complex quantum dynamics in order to show that we can perform more precise measurements. And one way that we've applied these ideas to a real system is, for instance, in collaboration with a lab at McGill, which works on studying little individual spins in diamond. And they shine lasers on those spins. They manage to determine the states of those spins in a way that can allow them to sense the magnetic field, say, coming from a single cell. And so we've shown that we can improve the speed of that operation. We can also show that we can sort of understand the complex quantum dynamics of these systems in a way that allows us to send quantum information from one system, in this case a superconducting system, into another system, in this case a spin system. We're also looking at ideas of quantum mechanics in thermal equilibration. So equilibration can occur through, say, thermally activated processes, hopping over a barrier, quantum tunneling, but we're also looking at many particle phenomena, these phenomena that involve quantum entanglement and how those influence the speed of equilibration, with ideas that with a view to ideas that might allow us to solve problems by finding the ground state of some other system. Quantum technology, although it's definitely a curiosity-driven field, has been noticed now by private industry. So a large number of companies just over the last 4 to 5 years have started investing very heavily in this area to try to push it forward and think about making it really practical within some reasonable time frame. So if there's one thing I want you to take away from this talk, it's that quantum mechanical systems are different. We can do more than just simulate classical behavior with quantum systems. We can actually use quantum rules or understand how we can use quantum systems to obey quantum rules to improve information technology. So thank you for your attention.
Thank you for the nice talk, Bill. I have a question about the state of the art. You maybe could tell us what is the largest number of qubits that have been successfully coupled together with some high quality. It's changing very fast, so I'm not up to speed.
Yeah. So to my knowledge, the best of my knowledge, I believe the record. Okay, there are many different measures and many different kinds of quantum states, but one of those quantum states is called a Schrodinger's cat state. Where you might want to prepare, so if you have many qubits, you can say prepare the qubit in the excited state or prepare the qubit in the ground state. If you have 2 qubits, you could prepare it in some state that is either 2 qubits in the excited state or 2 qubits in the ground state. I believe the record is still doing this with 14 qubits, which was done in a trapped ion experiment, so in Innsbruck, Austria. There are many other experiments where they generate other types of quantum states with many more particles, but it's difficult to compare one to another because the types of quantum states are so different.
Yes, I've got a follow-up question to that then. So why do the quantum dots, why do they need to be in the same location? Why can't you have a few quantum bits here and a few quantum bits in Vienna and a few quantum, and like kind of...
That's a fantastic question. So it's true. If you can convert the information associated with a quantum bit over here into, say, light, and carry that light over some distance, and somehow entangle the two quantum systems, then you can actually use quantum systems that are distributed across a very, very large length scale. So a group just last year, a group in Delft in the Netherlands, showed that they could get entangled states of 2 individual spins into diamonds that are separated by about 3 meters. So those 2 diamonds were in some kind of quantum state that you cannot describe classically, and they were able to show that very explicitly, that they really did achieve this kind of quantum state distributed over 3 meters. And in principle, if you connect these things with fiber optic cables that are much longer, you would be able to do it over an arbitrarily long length scale, provided you can really send the information accurately.